Hi everyone, in this video we're going to review the basic vocabulary and the key features of exponential functions as we begin our Algebra 2 unit on exponential growth and logarithms. So let's begin with the basic structure of an exponential function. We saw these in Algebra 1, f of x equals ab to the x. In a function like this, ab to the x means I have some initial value a. That is what my function is when x is 0. And as x approaches infinity, I am multiplying by the same growth factor, which would be b. I'm multiplying by b over and over and over and over again. So if my growth factor is greater than 1, then I'm going to increase exponentially to the right. And as I approach negative infinity, we can think of it like we are dividing by that growth factor. So I get smaller and smaller and smaller, but I never cross 0, right? Because no matter how many times I divide by a positive number, I'm going to get a very, very, very small fraction. And so this would be how basic exponential growth looks. My a value would be my initial value. My b value dictates how quickly my exponential growth is happening. That's my growth factor. And the other thing that we looked at in Algebra 1 is if my growth factor is less than 1, let's say I have something like f of x equals 2 times 0.5 to the x. If I have a growth factor that is below 1, or if I have percent decrease, for instance, then I may have an initial value, but that would mean I have exponential decay. So exponential decay may look like this. As x approaches infinity, then exponential decay would approach 0, and it would get smaller and smaller and smaller. So our key takeaways from Algebra 1 was that our initial value is the output when x equals 0. In the past, that has just been our a value. We'll come back to that shortly. And then our growth factor, and I'm going to say growth / decay factor, is b. When b is greater than 1, we have growth. If b is between 0 and 1, we have decay, because we would be multiplying by a fraction and therefore getting smaller over time. So far, these are the basic concepts we remember from Algebra 1. What I want to highlight on both of these graphs, and this is an important key feature as we move into Algebra 2, is notice that neither of these graphs ever extend into the negatives for their y values. This is behavior that we call an asymptote or asymptotic behavior. So think of our end behavior. In the past, we've said things like as x approaches infinity, the polynomial approaches positive infinity or negative infinity. On these graphs, on our purple growth function, as x approaches negative infinity, notice that f of x is not approaching negative infinity or positive infinity. F of x is approaching 0. So that is what's called an asymptote. As we approach infinity, our function is approaching a specific number. It's not going up to positive infinity or down to negative infinity. It's just getting really, 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 really close to 0 forever. Or in a decay function, as x approaches positive infinity, f of x is approaching 0. So both of them spring off into infinity on one end, but the other end is what we call an asymptote. It's approaching 0 instead of anything else. This is the first thing we are going to add to our equation in Algebra 2, is instead of just having f of x equals a times b to the x, I'm going to delete my decay graph. here. So let's just consider our growth function for a moment. Instead of f of x equals a b to the x, let's imagine for a moment we had f of x equals a b to the x plus 2. I'm going to say plus k. So if my equation has a b to the x plus k or minus k, what k is going to do is k is going to shift our entire function up at every single point. The result of that is going to be that instead of our function approaching 0, we're going to have an asymptote at a different location. So let's say our k value was 3. Then the entire graph is going to shift up 3 units. And now we're going to have an asymptote at 3. This graph will never go below 3 if everywhere is lifted up 3 units from the original function. So what's also worth pointing out is that our initial value also shifted up by k. So let's refine our initial value definition for a moment. Earlier we said our initial value is the output when x equals 0. In terms of our function equation, I'm going to define our initial value now. Instead of just as a, our initial value is a plus k. It is that value in front, but if we have a vertical shift, if we have an asymptote, a is going to be above or below that asymptote. Think of the asymptote as like our starting place, and our initial value is above or below that. So let's look at some, actually one more piece of vocab, and then let's look at some concrete examples. We have initial value. We have our asymptote. And this is at y equals k. And then, in addition to a growth and decay factor, we also have a growth or decay rate. So growth or decay rate is if we describe our growth or decay in percent change. So just like we did with geometric sequences, if my growth factor is 1.2, my growth rate would be 20%. If my growth factor is 0.5, my decay rate would be 50% decrease. So a rate is just referring to it in terms of percent change, whereas a growth factor is what you're actually multiplying by. But let's look at, let's give ourselves an example of this. So let's say I have, the function g of x equals, let's say our initial value is, our a value is 4. Let's say our growth factor is 1.25. To the power of x. And then let's say we have a k value of minus 5. Right. So first what I'm going to do is my asymptote is going to be at negative 5. So if I'm asked for the equation of my asymptote is at y equals negative 5. And this asymptote is so important, I want to literally mark it on my graph with a dashed line. So I'm realizing these are not exactly where they should be. Let me redo this so they're on grid lines. There we go. So I have an asymptote at y equals negative 5. What that means is if I go down to negative 5, I'm going to mark my asymptote by putting a dashed line like this. And I'm going to label this y equals -5. What that tells me is that that is the value that my exponential function is approaching on one end. And so if it's hard to see, if I have sloppy handwriting, you always want to mark your asymptote because think of it like it's just as important as a y-intercept or a 0. It's an important key feature of your graph. Then I'm going to imagine for a minute that this graph did not have an asymptote. It starts with 4, then I multiply by 1 1/4. That would give me 5. 5 times 1.25 gives me, let's see, 6.25. So let's say I have my exponential growth like that. Those values would be up here, but all of them are also going to drop down 5. So my initial value is 4 above my asymptote. And then my kind of like exponential curve is going to behave like that. So these individual points you can, of course, always look up. Like when you're asked a graph, you can look these points up in your table. But you want to think of an exponential graph as always mark your asymptote. And then when you're plotting your points, you are showing that you have exponential growth that approaches that asymptote in one direction and approaches infinity in the other direction. And the key values that you want to show are the y-intercept, so our initial value here would be 4 minus 5, which is -1. Our asymptote is at y equals -5. I would say this has a growth factor of 1.25, but this has a growth rate of 25%. So again, none of these things are super new except for the asymptote equation. But start getting used to the difference between a growth factor and a growth rate. Keeping in mind that your initial value will not necessarily be A. If you have an asymptote, that's going to shift your initial value up and down. And that all of these pieces are key pieces to show on your graph. So let's do one more with decay, and then you should feel ready to try your problem set. So let's say we have a decay function. Let's say I have h of x equals 10 times 0.75, or no, let's say 10 times 0.8 to the x minus 5. All right. Oh, we just did -5. Let's say plus 2. What I could do on this graph is if I look in my table of values, I'm going to see that my y-intercept is 12. So it's okay on a graph like this to scale differently as long as you scale intentionally. So maybe I'm going to count by 2s. If you count by anything other than 1s, always label and do so consistently so that your reader knows. So I have this graph. The first thing I want to do, I see an asymptote, so I'm going to put a dashed line there. The equation of my asymptote is y equals 2. So I have an asymptote at y equals 2. That means as my function approaches positive infinity, since this is decay, h of x approaches 2. And then my initial value instead of 10 would be 12. And I can get the rest of the points from my table, but the next point would be 10. And then how much is it going to go down from there? Then I'm going to be like here. And you'll see if you plot some more points in your table, always plot at least 3. We're going to have this exponential behavior where we approach our asymptote of 2. And we are decaying because we have a growth factor or a decay factor that is less than 1. So this would be my graph, and then my growth factor would be 0.8. And I'm going to call that a decay. You could call it a growth factor, but let's call it a decay factor because this is decaying. My decay rate, and sometimes they're a little tricky when it's decay. What I like to do if it's a decay rate is multiply 100 by 100 first to turn it into a percent. So 0.8 becomes 80%, and then subtract 100. We are losing 20% each period. So if I was asked for the decay factor, I would say 0.8 because that's what I'm multiplying by. The decay rate would be losing 20% per period. So hopefully this is a nice refresher of the key vocab to keep in mind. We will go into more detail studying each of these in this unit. But dive into the 4.01 practice. You can use your calculator for anything and make sure that you're labeling your graphs and your different pieces precisely.